After the Great Oxidation Event, Earth entered one of its most mysterious and extreme chapters. The sudden presence of atmospheric oxygen changed not just life, but the climate itself. Around 2.4 billion years ago, Earth was plunged into what scientists call snowball Earth, an era of intense glaciation that likely froze the planet from pole to equator. Ice sheets covered the oceans, and sunlight struggled to penetrate the white reflected surface. Life teetered on the edge, surviving only in deep-sea hydrothermal vents or isolated meltwater refuges. But even this extreme freeze would not last forever. Volcanic eruptions continued beneath the ice, releasing carbon dioxide into the atmosphere. Over millions of years, this greenhouse gas built up, trapping heat and eventually triggering a global thaw. As ice melted, oceans surged, temperatures rose, and the planet was reborn yet again this time, with a biosphere ready for innovation. Now, life exploded into new directions, from simple bacteria, more complex cells called. These cells had internal structures like nuclei and organelles, the architectural foundations of all multicellular life. Over hundreds of millions of years, eukaryotic organisms began forming complex colonies, then tissues, and finally, the stage was set for Earth's greatest biological revolution. About 600 million years ago, in the Ediacaran period, the first multicellular creatures appeared soft-bodied, and then, 541 million years ago, came the Cambrian explosion. It was like nature had suddenly turned on the lights in a relatively short period. Almost all modern animal groups emerged. Eyes evolved. Shells appeared. Predation began. Earth's oceans became a crucible of experimentation and dive. As life flourished beneath the sea, tectonic forces continued to reshape the land above. The supercontinent, Rodinia, broke apart, then reassembled into Pannotia. Mountains rose where plates collided, and deep rifts formed where they pulled apart. This continental drift affected climate, ocean currents, and even evolutionary paths. Earth was not static, it was alive with motion, a planet constantly reinventing itself. Around 470 million years ago, life began to leave the ocean. Plants were the first pioneers, creeping onto barren shores and transforming rock into soil. Soon after, the first arthropods followed: millipedes, scorpions, primitive insects. These brave organisms faced harsh UV radiation, noxious air, and unpredictable weather. But the rewards were vast sunlight, untapped land, and freedom from predators. Evolution favored those who adapted, and so land ecosystems were born. With plant life came another great shift. Oxygen levels surged, and carbon dioxide levels fell. This triggered global cooling, leading to yet another ice age. Mass extinctions followed, but each time life came back stronger, more varied, more complex. Vertebrates evolved from lobe-finned fish. Amphibians crawled onto land. Then came reptiles, insects with wings, and eventually, for over 160 million years, Earth was ruled by giants. Dinosaurs dominated every ecosystem, from towering herbivores to cunning, feathered predators. But beneath their feet, mammals small, warm-blooded, and nocturnal waited in the shadows. They were not dominant, but they were survivors. Then, 66 million years ago, everything changed in an instant. A 6-mile-wide asteroid slammed into what is now the peninsula. The impact was apocalyptic. Firestorms scorched the planet. Tsunamis tore across the oceans. Dust and ash blocked sunlight for months, collapsing ecosystems worldwide. The age of dinosaurs ended. But out of the ashes, mammals began their rise. Over millions of years, mammals diversified and spread across every continent. Primates evolved with better vision, grasping hands, and larger brains. In Africa, around 7 million years ago, a lineage of great apes began walking upright. These hominins would evolve into Homo habilis, Homo erectus, and finally, Homo sapiens. We are the newest chapter in Earth's 4.6 billion year history, and yet, in just a blink of geological time, We've transformed the planet more dramatically than any species before. We built cities, explored space, and discovered the very origins of our world. The same stardust that once floated in a collapsing cloud now looks up in wonder and asks, how did we get here? From cosmic debris to living planet, Earth's story is one of resilience, chance, and unimaginable transformation. It is the only known world to host life, and perhaps the only one that ever will. A fragile blue dot in the vast darkness, born in fire, shaped by ice, and animated by life. Earth is more than a planet, it's a miracle of time. Before Earth was Earth, there was nothing but chaos, gas, dust, and fire scattered across the void of deep time. Around 4.6 billion years ago, in an unremarkable corner of a spiral galaxy we now call the Milky Way, a molecular cloud, dense, cold, and ancient, began to stir. Something disturbed it. Perhaps the shock wave from a nearby supernova, the violent death of a star, sent a ripple through this calm sea of matter. And with that, the countdown to the formation of Earth had silently begun. This cloud, rich in hydrogen, helium, carbon, and heavier elements forged in earlier generations of stars, began to collapse under its own gravity. As it spun faster and faster, the cloud flattened into a disk, forming what astronomers call a protoplanetary disk. At the center of this cosmic whirlpool, most of the mass pooled into a hot, glowing sphere, the beginning of our sun. It was not Earth that came first. It was fire, and Earth, like all the other planets, would be the residue, the scrap from that stellar furnace. Within this rotating disk of gas and dust, particles began to stick together, tiny grains of silicate and metal bumping into one another, clinging with electrostatic forces. Over time, these grains became pebbles, pebbles became boulders, and boulders collided to form planetary embryos. The early solar system was not a calm place. It was a celestial demolition derby. Protoplanets slammed into each other at incredible speeds, breaking apart and reforming in a violent dance of gravity and motion. In the region between the young sun and the newly forming gas giants, one of these embryos began to grow faster than the rest. It swept up surrounding material with its increasing gravity, shaping itself into a sphere of molten rock. This was a newborn world of fire and metal, bombarded relentlessly by other bodies still hurtling through the system. Every impact brought more sand, more chaos. One such impact would change everything. About 4.5 billion years ago, Earth was struck by an object roughly the size of Mars. Scientists call it Dea. This wasn't just another collision. It was cataclysmic. The impact was so intense, it vaporized vast sections of Earth's mantle and sent a torrent of molten rock into orbit. Over time, that debris coalesced into what we now call the Moon. The Earth was shattered, remixed, and reborn. And in this rebirth, something miraculous was set in motion. In the aftermath of Thea's strike, Earth was a seething magma ocean, covered in lava, bathed in poisonous gases like methane, ammonia, and sulfur dioxide. There was no blue sky, no oceans, no land as we know it. But beneath that hostile exterior, something was stirring. The heavy elements, like iron and nickel, began sinking toward the center, creating the Earth's core. Around this dense heart formed the mantle and crust. This layering process not only defined the structure of our world, it created Earth's magnetic field, a force field that, billions of years later, would protect life from deadly solar radiation. As the molten Earth cooled, volcanoes burst from its surface, belching carbon dioxide and water vapor into the atmosphere. For millions of years, this release continued, transforming the planet's air into a thick, choking shroud. But it was precisely this noxious cocktail, this early atmosphere, that allowed clouds to form. And then, for the first time, rain fell. It wasn't a soft drizzle. It was a deluge that lasted for centuries. Torrents of water poured from the sky, filling the basins and scars left by ancient impacts. The world was cooling, hardening, and changing. Oceans were born. These primeval waters covered most of Earth's surface. They were not clear or calm. They were hot, acidic, and bubbling with minerals. But they were essential because inside them, the building blocks of life were coming together around hydrothermal vents on the ocean floor, where heat and chemicals erupted from beneath the crust. Organic molecules began to form amino acids, lipids, simple sugars. These were not yet life, but they were close. The Earth, at this point, around 4 billion years ago, was entering a new Agedahadian era. Named after Hades, the Greek god of the underworld, it was a hellish time. Meteors still rained down, many bringing new materials, including water and complex carbon-based compounds from deep space. The planet's crust was unstable, breaking and shifting constantly. Yet amid this chaos, Earth's surface began to solidify into stable rock. Continental seeds called cratons began forming, the beginnings of the land we know today. Then, around 3.8 billion years ago, Earth crossed a boundary, somewhere in a pool or vent or muddy puddle. The line between chemistry and biology was blurred. Molecules began to replicate. Not perfectly. Not like life as we understand it. But the process had begun through trial, error, and time. Self-replicating systems developed. And with replication came this early life was simple, nothing more than single-celled organisms. They floated in the oceans, feeding on chemical gradients and sunlight. But even the simplest life has power. These early microbes began releasing oxygen as a waste product of photosynthesis. At first, this oxygen bonded with iron in the oceans, forming massive deposits of iron oxide. But eventually, it began to seep into the atmosphere. Slowly, molecule by molecule, Earth was being transformed from a reducing to an oxidizing environment. Around 2.5 billion years ago, this change reached a tipping point in what scientists call the Great Oxidation Event. Oxygen levels spiked, and for many organisms, it was lethal. But for others, it was an opportunity. Oxygen was more efficient for energy production. It enabled more complex structures, more diverse life, and eventually, during this time, Earth's surface continued to evolve. Plate tectonics reshaped the continents, pushing land masses together and tearing them apart. Supercontinents formed, first Kinnaland, then Columbia, and later Rodinia. Massive mountain chains rose and crumbled. Volcanoes continued to erupt, altering the atmosphere and climate. And throughout it all, life adapted, diversified, and endured. Earth had become more than just a rock in space. It was now a world with oceans, an atmosphere, continents, and life. But the story was far from over. The planet still had to face global freezes, extinction-level impacts, and the long, slow rise of animals. The Earth, as we know it, was only beginning to take shape. What started as a cloud of gas had become a living planet. But how did this world, forged in fire and chaos, come to host trees, birds, and human beings? The next chapter of Earth's story takes us through ice ages, oxygen surges, and the rise of complexity, from slime to civilization. The second half of our journey reveals just how unlikely and miraculous our planet truly is.